Good morning, good night, good evening, everybody, and I hope you're having a good one, good day, and welcome to join me. Listen to the upcoming 2 lectures regarding the tight binding model for solids. So, of course, the course is solid state physics, and we are now in our lectures regarding the chapter 7.4. So, what we will do in the very next 2 lectures is that I will try my best to introduce to you a common method to understand the properties of solids, so electronic and optical properties of mostly dielectrics. That will be in our focus right now, so not as such semiconductors and metals, but rather dielectric materials. And I will introduce to you a tight binding model, or TB model, or just TBM for short. And of course, the approach is similar to the nearly free electron model or the free electron model. And in fact, both approaches can be used, or any of the approaches that exist out there can be used to understand the properties of solids. But maybe the tight binding model and the kind of like a philosophy behind it, it's more appropriate for dielectrics, because as we know, dielectric materials, they do not conduct electricity that much. So if we think about the kind of possible electron wave functions, they don't seem to be as such as plane wave looking quantities, but rather more like concentrated, localized wave functions. So and from this point of view, the tight binding model or the linear, what's the other? Linear combination of atomic orbitals, LCAO might be, where the electron wave functions are more localized in nature. So instead of like thinking of free electrons, we are now more interested in localized electrons and trying to understand how they would give rise to the optical and electronic properties of solids. But of course, as in all the approaches, we're essentially solving the Schrödinger equation, so that doesn't change into anything else. It's just a kind of like a slightly different philosophy that we're using. How do we solve the upcoming Schrödinger equation? And we will approach the problem by just using a one-dimensional case. So of course, please note that in principle, the generalization is rather straightforward, although mathematically it's not as nice and transparent. So that's why I chose that it's better to start with the basics. But let's now get started. We have a lot of things to cover, and first I want to just like highlight to you the kind of main philosophy behind this chapter and this section. And I will start with the very basics regarding tight binding model for solids and what comes to mind regarding that. So, like I said already, many different methods exist that we could use to understand the properties of solids. And essentially, what we are aiming to understand here is not as much as the thermal properties, but rather the kind of electronic properties and how different band structures are being formed and how they dictate the properties of materials. Oftentimes, the starting point is an empty lattice approximation, and this is many times a very good starting point because it does provide us the backbone of dispersion relations. So I really recommend that if you want to become a, level 29 solid state physicist, like a very high, very good solid state physicist, that's what I was trying to say here, that you should maybe start by forming a better understanding of empty lattice approximation in a 2D case and for different kind of 2D lattices, and then one by one, little by little, you move into the full 3D picture. Other approaches, as mentioned, the nearly free electron model, that's also quite much used, and it's quite good, especially when we try to understand metals and semiconductors. But there, let's just note to us that we are more focusing in the nearly free electron model into electron wave functions that are not as localized, but rather more free, as the name suggests. So we are solving the Schrödinger equation, and in specific, we are looking for solutions that look like plane waves, and that's the approach. But mathematically, of course, we know, like we remember the Fourier transform, that of course, if you just take enough of plane wave components, we can construct something that is very localized also. So philosophically and fundamentally, there's nothing restricting this approach, nearly free electron models, and just summing over many different kinds of plane wave like electron wave functions. We could also generalize this approach to dielectrics, but maybe we would just need to take in a lot of plane wave components, and then the summations become more cumbersome. And because of this reason, other approaches are often used when we are describing dielectrics. And when we are thinking of dielectrics, let us distinguish between metals and semiconductors and dielectrics. That in dielectrics, the electron wave functions are more localized in nature. And this, of course, nicely complies with the intuition and like real life knowledge that the dielectrics, in other words, insulators, they don't conduct electricity that much. So from that point of view, it makes sense that the electron wave functions are rather more localized in nature, and they don't participate in electrical currents and formation of them inside the materials. So often used approach is this so-called linear combination of atomic orbitals, so LCAO. I was right. And this essentially is very similar to what we will introduce here next in the upcoming 2 lectures. And as the name suggests, we're operating on atomic orbitals, so orbitals that are very close to the orbitals that we would have for an atomic substance. So we're kind of slightly modifying the kind of solutions of Schrödinger equation that we would solve for a single atom. And we know what kind of energy stage, what kind of electron wave functions we have associated with a single atom. And then we slightly modify those states so that we can actually describe now a material that is formed out of n atoms. So this is the philosophy that we're using right now. So we're kind of like not working on plane waves, but rather localized atomic orbitals or something that are mathematically similar. And here, what we are introducing to you is so-called tight binding model, TBM, and this is used, as mentioned, a lot with dielectrics because they are the most dominant contribution into the kind of properties arises from localized electron wave functions. And we will focus here in tight binding model, and we will apply it into simple cases, and hopefully we can understand a little bit about dielectric solids from the kind of quantum mechanical and solid state physics point of view. And please remember this, in dielectric solids, the electrons really are quite localized in nature, so this also kind of motivates and justifies us why we are using a slightly different approach than the nearly free electron models and so forth. But of course, everything would work out if you would just do things properly. And I will also mention that this tight binding model could of course be used to understand also metals and semiconductors, but then we would just need to extend the basis that we are using so that we would have more and more or different kind of wave functions. And I guess how the nature works is that somehow, like, these are of course models, but somehow Mother Nature seems to be behaving in kind of like, I don't know, in a way that is somehow a mixture of all of these approaches in a way, or somehow like or how could I rephrase it? Maybe I don't try to rephrase this, but just that the kind of principles, how things actually work out, they are of course slightly different than what we are kind of trying to build using simple mathematical models. But this is the kind of main outline and main motivation behind this section 7.4. And let's now get started with the first part of the lecture. So the first lecture where we are forming a tight binding model for a one-dimensional chain of atoms. And as I promised, we always start with the Schrödinger equation, as with all the techniques, all the methods that we have introduced and we could introduce to you in order to understand solid state materials. So we have a Schrödinger equation, and this time we write it in a operator form. So we have this Hamiltonian operator that is operating on our total wave function psi, and this total wave function is now the wave function describing the whole material we have at hand. And then on the right-hand side, we have the energy operator E hat that is operating on the same total wave function of our system. So this is the kind of wave function associated with this one-dimensional chain of many, many atoms. For simplicity, as I promised, we restrict our treatment to one-dimensional periodic chain of atoms, and we have n atoms in total. So each atom here, and this is also assumption we make, we assume that each atom exhibits only a single electron or molecular orbital, and we denote this molecular orbital by I. So if you are familiar with the bracket notation, this is a ket of I. And physically, this means this corresponds to an ith atom's orbital. So that's the kind of like we have n atoms, and this one ket I is essentially the ith atom's electron's state, the single orbital it can reside in. And we assume now, in what follows, that these orbitals are entirely orthogonal, and this would give us a relation that we would have a bra over nth atom's orbital, so a bra of n multiplying the ket of m, and this would be, of course, a Dirac delta function. So the result of this bracket would be non-zero only when n is m. There's a kind of point of subtlety here. This is a very strict mathematical condition, and this is highly useful to us in what follows. But I should mention to you that this is, of course, some kind of approximation we physicists make in order to make the math slightly simpler. Because, like, after a while, we also we add into this model a possibility that an electron can hop from the nth atom to the mth atom, so that the kind of electron states can move around slightly in the system. And of course, it's entirely obvious that if this kind of hopping can take place, these orbitals cannot really be orthogonal, because it wouldn't be physically possible that the electron would move from a different orbital into another one. So there is this kind of approximation that we are implicitly making here, that we kind of approximate that they are almost orthogonal, so that we don't need to care that much, or we can simplify math by using this kind of condition. But on the other hand, we should keep in mind that this is not strictly valid. So this is not a course on mathematics, but this is a course on physics, and this is just a nice approach, nice method to approximate, or nice assumption to approximate, or find a good, easy, approximatively solutions out of our Schrödinger equation. I hope I was able to clarify. In case I'm not, please talk with me, discuss with me what I meant here. But please remember that this is just an assumption, and it's approximation at best. So now we have a possibility to form the general wave function, and this, of course, this general wave function would mean that it would tell us where all the electrons in the system are. And since we have n atoms, so we have quite a lot of electrons here. So that this general wave function is actually a vector that has quite a few components inside it. In many systems, we have electrons of the order of Avogadro's number, so 10 to the power of 23. So needless to say that many times in practice, these would be insanely large, these wave functions, if you would think or try to solve things rigorously. In practice, we're not, and in practice, we are resulting to, instead of using vectors, we are actually thinking that we have a vector in a Hilbert space, and then we can change many of the calculations into integrals, and then that simplifies things. But let's get forward. So now we have a general wave function psi. That's the ket of psi, and then the kind of this wave function is essentially a superposition of those above localized orbitals. So mathematically, what I'm trying to say here is that this total wave function, general wave function psi, is a superposition, a summation over all of these mth atoms orbitals, and we have this phi n giving us a kind of weight or a coefficient of how much of an influence we have for this given orbital here. Or maybe I should clarify here, we are kind of interested still in a single electron's behavior. So we are assuming a single electron approximation. So here we are only treating a single electron, but it does exist in a system of n atoms. And then once we are done, we can start populating things by just adding things and forgetting the possibilities that the electrons could couple with each other and kind of modify systems. So we are still kind of like just assuming that we have a single electron, and then this weight term here would tell us the probability, essentially, or the modulo square of this would give us the probability that the electron would give in this single nth atoms orbital. And this weight coefficient phi n, of course, it's a scalar, so there's nothing to say that why we couldn't just move it from the other side of the ket of n. So that's what I'm trying to show with this equality here, so that we can move the scalar around. That doesn't change things mathematically. Now we assume that we have these orbitals, so we have these kets of n, and we assume that we can normalize them. And this, of course, physically would tell us that we want to ensure that this single electron we are interested does reside somewhere in the material system, in the chain of one-dimensional, like a one-dimensional chain of n atoms. So when we normalize things, we ensure that when we are summing over the probabilities, so those modulo squares of over phi n, we get a unity out so that the electron is somewhere. And we don't do this normalization, but we just assume that we can do that, and then we can calculate the weights so that the probabilities where the electron state is using this bracket, so that we have a bra of n multiplying the ket of the total wave function psi. And of course, this is essentially the same math we use to, for example, calculate the Fourier coefficients when we are calculating Fourier series or the coefficients in Fourier transforms. So in any integral transforms, this is the approach how do we do. So like it is, of course, could be turned into an integral. This is bracket notation. No problem about that. So please note, if you're more familiar with those kind of ways of calculating coefficients, like you could just think that this is exactly that equation. That's the means how do we calculate, for example, those Fourier coefficients. And now what we can do is that we can show with the above restrictions, so that we have orthogonality over the states and they're also normalized. We can show that the wave functions form a complete set. And what this means is that when we take the ket of a psi, the total wave function, and we can write that, of course, that it's the superposition of over those all orbitals. So we sum over n, the kets of n, and then we multiply with the phi of n. So this is the kind of weight that the probability related to the probability that the electron is in this orbital, and this, of course, the scalar phi n, the weight, can be written with the equation we got from above. So essentially we can use this equality, we place that there, and we'll end up with this kind of condition. And now we see that we have on the left hand side, we have the total wave function, the ket of that, and here we also have a ket, and we are summing over these, so that essence, so that this equality would hold. That would mean that the summation over these ket n's, ket bras over n would be essentially identity matrices. So this is the kind of logical conclusion that we get out. So that this kind of operation here gives us an identity matrix. I think I will leave this as a homework for you to show that how this completeness can be shown. I think it's a good piece of mathematics, and it helps us to understand how do we operate with these things, especially in this kind of quantity. How does it look like in practice? And then that helps us to form this relation and this fact that it's a complete set. And since we have a like normalized basis, physically, of course, this means that the electron, the single electron we're looking at, is somewhere in the system, in some of these states. So when we sum over the kind of weights, the probabilities that the electron is in any of these states, we get a unity out. So it's somewhere, the electron, it doesn't vanish. And of course, that's a kind of very, very intuitive notion physically. Let's now look next into the Schrödinger equation and how we can transform that into an eigenvalue problem. So we can multiply the Schrödinger equation from the left-hand side with the bra of n. So then we have this kind of looking term on the left-hand side of the Schrödinger equation. And then, of course, the right-hand side involving the energy operator, E hat, is then of this form. So essentially, we just multiply left-hand side from both with the ket of n, and this is what we get out from the Schrödinger equation. And now we can write the total wave function, of course, like using the superposition forms that we gave you previously. So then we get then a kind of left-hand side turned into a summation over m. That's just a dummy summation index of bra of n. And then we're still operating on the Hamiltonian operator. And then we have the ket of m. And then we're multiplying with phi of m. So essentially, we're just turning this total wave function. We are describing it as the superposition over all of these orbitals, atomic orbitals. And of course, we do the same thing for on the other side for the energy operator. And then we get this kind of condition here. And then we have this phi m there. I should have a prime here. Sorry, I have a typo. And then please, my arch nemesis, sunny side up. Please don't complain. I noted this. Apologies. And since we are summing over a dummy summation index of m prime. Well, seriously, I'm happy that people are finding mistakes from my slides and commenting. It just feels embarrassing, but I'm happy for it. So now, what we can write, the left-hand side, we can use a simplification notation. So we can just write this nasty-looking thingy here, in a more cleaner fashion. Let's not go into the details of what's happening here, but we just use a notation. We just simplify notation, nothing else right now. And then what we get on the left-hand side, this is something that we can actually simplify. So please note this ket of m prime is operating on the or maybe I should say the other way around. So this energy operator is operating on the state of m prime. So what we get out, of course, is that we have the eigenenergy of em out, em prime. And then we have the scalar. We can change the scalar to be on the other side of the brackets because it's a scalar. We can change the order. No problem about that. And then we are left with the bra of n multiplying a ket of m prime. And now we can take use of the orthogonality condition. And we know that this will be non-zero only when m prime equals to n. And then we can simplify this outcome that it's only giving us out a energy of En times the phi of n. So this is where we are using this orthogonality condition. And as I mentioned already before, this is of course cannot be exactly true, but let's just assume that it's approximately true, and then we can use this kind of like a simplification to make math more bearable. So we have used a simplification or simplifying notation. So this H and M is essentially this bra n, the Hamiltonian operator, and the ket of m. So in a way, it's a kind of matrix component, the nth component of the Hamiltonian matrix, if you're familiar with the kind of meaning of this kind of like a bracket. But most of the time, we don't need to go thinking about how they look like mathematically. So let's just try to draw bras and kets and be happy with that. So now what we have is that we have written the Schrödinger equation into a slightly cleaner form. So we are summing over m's, and we have this h and m terms there, and these, like I mentioned, they are the matrix components of the Hamiltonian operator, and then we have this phi m that is associated with the weight of the electron on this mth atom's orbital, and then on the right hand side we have the energy associated with this state n, and of course we are multiplying that with the phi n, that is the weight coefficient of electron being in that state. So essentially we drop the index E in n from the E energy because we don't need to have that specifically there. We have a single orbital in case, so we don't really need to like label the energies here that accurately. So we have the equation, and this is mathematically an eigenvalue problem, and that's always nice thing for a physicist to see, because now we know how we can actually solve this. And this is now associated with a non-trivial solution, like a solution we are seeking, not just a zero vector and matrix, when the determinant of this equation vanishes. So we basically are now able to solve the system by restricting or finding a condition for the energy that this determinant of Hamiltonian operator minus E times identity matrix is 0. So this is how we solve the eigenvalue problem. And please note, this approach, like we can solve it and we can find an accurate solution, but this solution is only the best solution that can be found in terms of the used orbitals we have started with. So we choose in the beginning, and we chose here that we are only having a single orbital associated with each of those atoms. So we could find a solution, but it would only be the best solution in terms of this used choice for localized orbitals. So that's the kind of restriction or limitation we have in this approach, especially in this stage. So if you're only considering like for example, s orbitals of atoms and nothing else, like the kind of upcoming physics will be slightly dull, because we cannot really try to see the physics that would be associated also having a p orbitals there. So for example, the group 2 elements, the alkaline earth metals, like we would have very much trouble in trying to understand their responses with this math we have formulated so far. So the time-binding model approach, like how we could extend that or generalize that or improve it, the approach is quite straightforward. So we would just add the amount of orbitals per each of those atoms, and we could use the kind of orbital functions that we use to describe the electron wave function nearby the mth atom or ith atom or nth atom. So for example, the mth atom's response, we could use a set of orbitals to describe where the electron is. So we could use an alpha term that would be kind of corresponding, for example, somehow on electron being in an s orbital or something similar, resembling an s orbital's electron wave function, or it could be something resembling a electron in a p orbital or a d orbital, and so forth. And this, of course, would result in an expanded set of basis vectors. So instead of just using a bras and kets of m, we should then also tell to you in which orbital we are thinking the electron is, since we would have a possibility that the electron would be in many different orbitals. And please let us be clear here. This means that we are dealing with, we assume that the electron of interest is localized in nature. We are trying to understand dielectrics here. So this means that we are kind of looking electron wave function nearby the nth atom in this chain of atoms. And this alpha then would mean that the electron may be, for example, in a orbital resembling an s orbital or p orbital or d orbital and so forth. And this is the kind of how we generalize the approach. And this is also nice, the time binding approach and the LCAO is that we can connect these orbitals and electron wave functions now with something that we are maybe more familiar from the chemistry courses, so that we kind of know roughly already, or we can imagine already that what kind of wave functions we're dealing with, and what kind of overall properties we would assume these orbitals would have. So at least I personally like this approach, so that it does provide a nice additional intuition to us. Okay, from the computational point of view, of course, making this kind of expansion of the basis set is really trivial. That's not a complication at all. The complication that happens is that the orthogonality condition that we assumed that works out for us is not a good approximation anymore. So essentially, mathematically, we cannot anymore do this kind of a trick with the mathematics, that if we would have this kind of a bracket of nth atoms electrons orbital, and we would then try to see that is there any overlap between the nth atoms and beta orbital, this condition no longer strictly holds, so that we don't get a kind of Dirac delta functions out. But on the other hand, maybe we can be pragmatic about this, that since this orthogonality condition was not entirely true to begin with, because we are looking for some kind of possibilities that the electrons are hopping from nth atoms orbitals into nth atoms orbitals, or between different orbitals in the same atom, so that maybe this price we pay is not that bad. That's what I'm thinking here myself. And then, of course, the resulting math, we wouldn't be able to most of the time get a nice eigenvalue problem out, but it would look something more similar to a generalized eigenvalue problem. But nevertheless, it will be a kind of matrix equation and vectors and such. So perfectly solvable using linear algebra and the computers and tools. So from that point of view, this is not that bad. And now, what we can do, and what we will do in the upcoming lecture, is that we will now solve how a single orbital case would look like. So I will just outline here the kind of overall mathematics, and then in the next lecture I will show how things look in practice in terms of calculations. So we have the Hamiltonian operator, and Hamiltonian operator, of course, it's a kind of total energy operator. So we have, first of all, the kinetic energy term. So we have the kind of modulus of momentum, so P modulus squared divided by 2 times n. So this, of course, gives us the kinetic energy of the electron, the single electron we're interested in. And then we have the kind of potential energies. And then now we are summing different kind of operators that depend on the kind of location where we're at, and the kind of other atoms locations. So we may have different kind of looking potentials here. And this is, of course, how we can generalize the approach mathematically. The kinetic energy term, we can also just label that's the kind of k hat kinetic energy operator, and then we're still summing over those potential operators. But we don't look into the details what kind of potential operators there are. We can multiply both sides with a ket of m, and if you can do this from the right hand side, what we have is that then we have the Hamiltonian operator h, and we are multiplying that from the right hand side with m, ket of m, and then what we get out is that then on the other side we have the kinetic energy operator, and that's being multiplied with the ket of m, and then we have the potential operators, and then of course they are being multiplied with the ket of m. So we can take out this one single potential operator there, that is when the j equals m, so that we can write one theorem that is of this form, and then the rest of potential operators we're still leaving inside the summation, so like this. So here we are just basically taking out a single potential operator for here for the case when J equals M, and then we can have this kind of term here, and then the leftover potential operators are here. And why do we do this? Is that now physically, like the first term that we have here, this corresponds to the Hamiltonian of a nth atom, like a single atom Hamiltonian. So essentially, this looks like now something that we would just have a single atom in free space, and we would calculate the energy states of that. So we would solve the Schrödinger equation for a single atom and for this single orbital case, and then we would solve that first term. And this is of course nice because we can solve this easily. It's its own eigenvalue problem, so that then we know that this first term corresponding to the single atom, the nth atom, we know that we can get out kind of like a eigenenergy epsilon at, that is the kind of like nth atom's atomic eigenenergy. So this is the kind of logic that we have here. So that this term can be very easily solved, because essentially it's in a one atom Hamiltonian corresponding to the nth atoms, and then we get the energy out. And this is nice because it really simplifies the piece of math quite a bit. And next what we do is that we multiply with a bra of n from the left hand side, and what we are left over is that we have this kind of looking term. And please note, we had that simplification notation earlier introduced. It looks exactly like that we had before for the H and M. And now what we have on the right hand side, we have the atomic energy epsilon at, and then we have the Dirac delta function, so that we have that only in the case when n equals m. And then we have the potential operators, and they're of course multiplying all of those potential operators from the left hand side with the bra of n. So this is what we have now, and please remember that this term here, we already were describing, we were using the simplification notation for this guy there. So we had this H and M and in place already, and now we have exactly the formula for how do we calculate that. And we already can solve these out, or we can look from the literature how these energies are. And then the kind of only question mark is that depending on the kind of assumptions we make, what kind of potential operators we have here, and how do we solve subsequently then the eigenvalue problem. But that I will leave to the next lecture. How do we do that? So I thank you for following this lecture, and I hope it was interesting and it introduced you the basics regarding the tight binding model. This is really nice, and it's not that bad in terms of understanding how things work. It's quite intuitive once you think about it for a while. So I thank you, and please join me quickly in following the upcoming lecture. Thanks.